Alright, hello everyone. Today we are going over forces and fields. Specifically, we're going to go over magnetism. Alright, opening up to you guys. What do we know about magnetism? Let's get some ideas going, write some things down.
They're fun.
Fun, sure. Magnets equals fun.
Things.
Fun.
They interact and repel.
Repel, yeah.
Attraction and
attract.
Yeah.
Anything else?
They stick to metal.
Stick to metal.
Some metals.
They kind of self-orient.
Someone's print. Is there a printer down there?
Alright. Don't know what that
What
printer
is
is
that?
doing.
Thinking real hard.
But overall, what really is magnetism? Now, think of magnetism as something we can observe. It's not a good way to describe what it is. When we have magnetism, we notice that we have charged particles, and the charged particle, like we learned in electric fields, creates its own electric field. So if we have moving charged particles, has an electric field. But this charged particle, when it moves, because it's a charged particle, it creates magnetic field. Now, magnetic field is given to us by letter B. So magnetism is originated from moving charged particles, which in effect create a magnetic field. This is something we can observe. So if we think about the Earth, our Earth has a magnetic field too. So we can think of it having a giant bar magnet. Now for magnetism, there's two ends, just like there was a positive and negative in electric fields, we have a north and south of the magnet. Anyone a little bit confused right now why I drew this upside down?
Yeah.
Yes.
You see, our Earth, north pole of our Earth, by orientation, geographic, is actually the south pole of our magnet. So when we have a compass, and we want it to point north, let's say this is a compass, I know it's kind of a lame compass. We have the fundamental thing that opposites attract. So our north end of the compass will want to point to the south magnetic end, which is our geographic north pole. Now, as far as a field of a magnet, what we have is by our, what's the word? Nomenclature, by what we draw, things flow out of the north and into the south. Now, strength of field changes with distance. The farther we get away, the weaker it gets. Our whole Earth operates like this as a magnetic field. And these magnetic field lines are what is observed. Now, the Earth is a magnet because the Earth inside, it's not solid. It's actually at a core liquid between a mantle and a very solid inner core. The core is solid, but the mantle is moving, it's conducting. That creates a magnetic field because the charges are moving. Charges move and give us the magnetic field that we observe. Now it's hard when I'm discussing to see what a magnetic field looks like. So, one thing we should know about magnetic materials, do we know anything that's magnetic?
Fridge.
Fridge, all right. Think about elements, chemistry.
Copper, iron.
Iron, that's one.
Isn't cobalt?
Nickel, iron, cobalt, nickel. There we go.
Yeah.
So we have some iron filings. Blow that out. Got a magnet underneath. And I'm going to pass this around.
Whoa.
And you can see the magnetic field interacting with these iron filings. Now go ahead, give it a try. Have a little bit of fun with it. So what's happening while you guys pass that around we have our bar magnet. North, south, and we have our iron filings around, and these are, if we're looking at a magnet, are aligned with the magnetic domain of this magnet. So we have these little iron filings that will line around our magnet, and that's what you're observing there on the plate when you're passing it around. Because iron, like we discussed, is one of our magnetic materials. Now I should emphasize these are permanent magnetic materials. There's other ones that can have a temporary magnetism, like aluminum, but we're not going to go into that today. What I'm really interested in doing is going over just an introduction of what we're going to be doing later qualitatively. So we are going to be going over Lenz's and Faraday's law. Now, we discussed this one a little bit earlier. Lenz's law, does anyone have an idea of what that is? So, if I have a changing magnetic field, let's have,
Question for you, Jason.
yep, question.
With these ones, are they orientating themselves to flip toward the magnet?
Yeah, flip towards
So
the
they
magnet.
have each in their own properties?
Yeah, so what you're seeing there, so the magnets like this underneath, you think of a north, south, and the iron fillings are aligning to the magnetism of the magnet itself. So they're being attracted and repulsed. Iron fillings here being attracted to the end. So if we had a little iron filling, this would be now north, south.
So the iron feelings are orientating, do they orientate themselves?
Yeah, they orientate themselves to what the magnetic field of the magnet is.
Okay.
Now, what I was going over here.
What?
Lenz's law. So pretend we have a loop of copper, which has electrons in it, because we have free charge carriers in copper. We've been over this in electric fields. And we have a magnet that passes through it with its magnetic field. What Lenz's law states, this being magnetic field, these being loops, we're going to call these loops N. And this loop has some area. What Lenz's law states is that when we have this magnet passing through, any change in our magnetic field is going to produce a change that is equal and opposite to oppose the magnetic field that exists in this magnet. So if the change is going to be equal and opposite, if I bring this magnet in this way, what is the direction of the magnetic field created to oppose that change? Remember that magnetic field for the magnet is coming out that way. So what direction is magnetic field being created to oppose this change? That way. Now relating this to Faraday's law, I got a bit ahead of myself there. This term being flux, and that's just a weird symbol of physics that you're going to have to accept, that this symbol means flux, is equal to the number of coils, N, times the magnetic field of our magnet and the area it passes through. Now what Faraday's law says is that if we change that in time, we're going to create an nth, also called a voltage. Remember from our unit on electric fields that we have a voltage associated with an electric field over some distance. So we have, this is our weird symbol for M, if we're thinking about what we learned already, that is actually our voltage. And that says our change in flux over some time will produce an M. So we have this one, which is Faraday's. And this one, which is Lenz's. Now, I'm glad we're through the preamble, because now it's time to show you the demonstration. Be aware, guys, I am going to be turning off lights. Before I do, I should show you what I have here. Right in here, just like I showed you on board, we have coils of copper wire. Inside here, I have a magnet. This magnet is going to spin, and we're going to see what happens. Do we have a prediction?
Magnet. The magnet's gonna spin.
Yeah, magnet's going to spin. The magnet, around the magnet is copper coils. So they're attached to this light bulb.
It's gonna create an electric current, so the light's gonna turn on.
Yeah, it's going to create a voltage, so the light's going to turn on. Pretty good prediction. Anything else?
I'll make notes.
All right, let's take a look. Oh no. Oh well. Well,
Did it work?
let's turn it
What
off.
fell off?
Let's see if I can attach it on super quick.
It blew it off.
All right, let's give this one more go. Now, can I have you hold that light there?
Oh, cool.
All right, so let's see what we observed here. Let's turn our screen around and also our video. So, the faster I turned it, looking at Lenz's law, what do you think will happen when I pass this magnet through faster? The same thing you just demonstrated with the light bulb. Any guesses?
The faster it goes, the more current.
Yeah. So, light bulb gets brighter.
The faster you go.
How else can I make this light bulb brighter?
Move it.
More loops.
More loops. If I had more loops, I could make this light bulb brighter.
Oh.
How about increasing the area of the loop?
So if you increase the size of the loops to get more area inside?
Yeah, if we have more area, there is more magnetic field that can pass through it. Greater electricity. Over here, you see we don't get nearly as much light.
Should I go
Anchor
faster to
rod.
get that?
What's the last way we can make this light bulb brighter if we wanted to? And it has to do with our magnet here.
Do you have a longer coil tube? Like more coils?
Yeah, we had more coils. So someone said there, if we have a stronger magnet, we can make this bulb brighter. All right, so we're gonna get into that more later, more quantitatively, but right now this is our qualitative understanding, and as we get into it, we're gonna get more into the numbers. So quick thing, what is Lenz's law? If we produce a magnetic field into our coil, what's going to happen? Anyone?
Flux.
Yeah, flux. So it's going to produce a change to oppose magnetic field that we created. And Faraday's law says what? That if we have this flux going through our coil, we're going to
Get a current.
get a current, light up, we're going to get a voltage, an M, which is displayed as a light bulb lighting up. All right, we will get into that more next class. Please review this stuff because we will be getting into the numbers of it. All right, thank you.